In this section, we're going to do something that seems a little out of order. If you remember when we did mechanics first, well, we didn't have any rotation. We basically started with kinematics, which we did here. We described the motion, position, velocity, acceleration of an object in terms of rotational variables. And then we went on to using forces to show how the change in motion was created. After that, we went into energy. So we're actually going to start with energy first, and then go to what would be the equivalent of force in rotational motion, and that, of course, is torque. So we'll start with energy, conservation of energy. We'll see how mass is being replaced by rotational inertia here. And then we're going to go back and talk about essentially Newton's second law for rotating bodies. So if it looks a little out of place, it is. And we're going to start with energy first. Okay, so if you remember, we said that instead of having mass, which is a measure of inertia, rotational motion, we had something called the moment of inertia, which is essentially the rotational version of mass. Mass tells us how difficult it is to change the motion of an object. So moment of inertia is going to be the resistance to the change in rotation. Now, when we're looking at the moment of inertia, we're going to do calculations in the next chapter and talk about that. The SI units for rotational inertia, or the moment of inertia, are kilograms times meters squared. Now, that's because our moment of inertia, is actually the sum of all the individual masses of an object, if we break it into individual parts, times the distance that that mass is from the center of rotation. Now, the more distant a mass is from the center of rotation, the more torque it's going to require to put it into motion or to change its motion. Now, another way of looking at the moment of inertia is to integrate over all the infinitesimal masses times their distance from the axis of rotation. And again, we'll get into this in the next chapter. But again, think about the moment of inertia in terms of how the mass is distributed with respect to how far it is from the axis of rotation. Okay, now the kinetic energy for rotation can be written similarly to the way that we did translational kinetic energy. We had Ke, or K, is equal to 1/2 mv squared for translational motion. Now we replace the m with an I, we replace the v with an omega, and we still get the same units we had before. 1/2 m, that's kilograms, times v squared, which is, of course, meters squared per second squared, has now become kilograms meters squared divided by seconds squared. So we're the exact same thing. We're still having a joule for a unit of energy, or SI unit, which is the kilogram meters squared per second squared. We've just moved the meters squared into the I, and we're left with omega squared, which is radians squared per second squared. Radians are dimensionless. Now, conservation of mechanical energy, if there are no non-conservative forces, nice double negative there, states that the energy, the mechanical energy before, is equal to the mechanical energy after. Now we have to include not only our translational kinetic energy, our 1/2 mv squared, with our rotational kinetic energy, 1/2 I omega squared, and our potential energy, which doesn't change, it's still mgy. It doesn't really care about the rotational position. So this sum before is going to be equal to this sum after, as long as we don't lose energy through non-conservative forces. Let's take a rolling wheel, okay? Now, we saw before that if this wheel is rolling along some surface and the surface is in contact such that the surface of the wheel has to rotate with the surface that it is in contact with, that basically it will rotate such that the velocity of the wheel is equal to r omega, or basically omega is equal to the velocity divided by r. They're both connected that way. So with this rolling wheel, we have two different types of kinetic energy. We have the kinetic energy associated with the center of mass. And for a wheel, the center of mass is actually located at the center of rotation, or the axis of rotation. Okay, so that center of mass is going to move, and the kinetic energy associated with that translational motion is just simply 1/2 mv squared, where v again represents how the center of mass is moving. But we also have this rotational energy. And as this rotates, if the surface of the wheel is basically restricted to move with the surface of the ground, this v is going to be equal and opposite to the velocity of the center of mass. Or I should say the velocity of the outer surface of the wheel moving with the ground is going to be equal and opposite to the velocity of the center of mass with respect to the ground. Okay? So when I take a look at this equation right here, I can actually connect different quantities. I can relate the mass to the moment of inertia. Okay? That depends on the shape that we have of the rotating object, but we'll get into that in the next chapter, how we come up with those relationships. But more importantly, I know that v squared is equal to r squared, omega squared, because once again, v is equal to r omega. So let's take an object of some mass. I'm going to find out that the mass doesn't really matter. And we're going to say that this rotating object, this ball, for instance, must roll down the hill such that the surface of the ball moves with the ground underneath it. Okay, it starts at 10 meters high up this ramp, and as it rolls down, we are going to get both rotational kinetic energy and translational kinetic energy. Now, without saying where this number came from, we're going to say that the moment of inertia for a solid homogeneous ball, okay, isomorphic, is 2/5 mr squared. Okay, I'll show you where we got that in the next section, but we're going to just accept that that's the fact. How much energy is converted from potential energy to both translational and rotational energy? Well, I know at the top of the hill, all my energy, if it starts at rest, is going to be gravitational potential energy. But remember, that energy now has to be turned into not only translational energy, but also rotational energy. It can't slip. And if we make the proviso that it cannot slip, V is equal to R omega. So our energy before equals our energy after. No mechanical energy is lost, so I can say this. Also, I can say if the ball starts at rest, this part and this part of the equation are going to be 0. So I get that the mass times acceleration times the height, okay, mgy, is going to be equal to the energy that goes into rotation and translation by the time it gets down to the bottom of the hill, where the total potential energy is 0. So here's my potential energy. Here's my kinetic energy, translational. Here's my rotational energy, which is kinetic. Now, notice what I've done here is I've taken 1/2 I omega squared. I said I is equal to 2/5 mr squared. Okay, I'm going to plug that in to this right here, this I. Okay, I get this value right here. And now I can plug in for omega, the fact that omega is equal to V over R. Okay, that means omega squared is V squared over R. And that simplifies my equation to this. Now, again, let's recognize the different parts. Here's my potential energy. Here's my translational kinetic energy. Here's my rotational kinetic energy. 1/2 of 2/5 is going to turn into 1/5. V squared over R is my omega squared. R squared cancels out with R squared. And we can now, since I have mass here, and mass here, divide both sides by mass. Mass doesn't matter in this equation, okay? The acceleration of gravity times the height at which it starts is equal to 1/2 V squared plus 1/5 V squared. Now, once again, this translational kinetic energy gives me the 1/2 V squared. But remember, some of the energy is going into rotation. For the solid ball, we get 1/5 V squared for representing that rotational kinetic energy. What I've done here is I've actually divided out the m. So this is the amount of kinetic energy per kilogram in terms of rotational energy. This is the amount of energy per kilogram for the translational kinetic energy. 1/2 plus 1/5 is basically 5/10 plus 2/10 is equal to 7/10. 7/10 v squared. I can solve for v here. I'll multiply both sides by 10/7. That gives me 10 times gh over 7. I take the square root to get rid of the square and the velocity. And I get that v is equal to the square root of 10, 9.8 meters per second squared times 10 meters divided by 7. That's 140. The square root of 140 is 11.8 meters per second. Okay, so that is the case for the ball, which doesn't slip. The ball basically rolls down the hill. What if, in fact, this ball were just to slide down this inclined plane? We've done that problem already. We've done that for an object sliding down an inclined plane and saw that the acceleration was equal to g times the sine of the angle, in this case, 30 degrees. Well, the hypotenuse of this, since the sine of 30 degrees is 1/2, that means that the hypotenuse will be twice as much as this. So it's going down 20 meters with an acceleration of 4.9 meters per second squared. I can use a kinematic equation to find that out, and that would be 14 meters per second, okay? In fact, if I go back to this equation right here, and I get rid of the rotational term and just make GH equal to 1/2 v squared and solve for that, this equation actually becomes V is equal to G times H, okay? Times, well, we'll have the factor of 2 here, so 2 times GH, 2 times 9.8 times 10. We roughly would get 1,000, and the square root of 1,000 would be 14. So I get the same exact results. Now, again, for a ball sliding down the hill where no energy is lost, okay, we'll say that the coefficient of friction here is absolutely 0. So I would get no loss of energy through friction. The ball at the bottom would be moving at 14 meters per second because it'd all be translational velocity. But with the rotational motion, it's actually going slower at 11.8 meters per second. Okay, now the ball was a special case. That had a moment of inertia of 2/5 mr squared. Different round objects will actually have different moments of inertia. So I can calculate the different results for different values here, different values for the moment of inertia, by generalizing this equation. Instead of substituting in something for I, again, I'll do the same approach. Here's where I started my last problem. And I'll just leave it as I, and we can see that the potential energy is equal to the translational kinetic energy plus the rotational kinetic energy. So that gives us this equation right here. I'll solve for V, divide both sides by m again. M doesn't completely come out of the equation, but I get here that my velocity squared is equal to 2gy over 1 plus I divided by mr squared. And again, what this shows us here is for different objects of the same radius, the same mass, the moment of inertia will determine how fast they're going by the end here. Okay, now, importantly here, we have to think about the way the mass is distributed. The moment of inertia tells us essentially how much this is going to resist any change in the rotational direction. So the more mass that's distributed away from the axle, the slower it's going to go. So if I have all these objects of the same radius, this hollow ring right here has all of its mass distributed a distance r. It has all the mass distributed at a maximum radius. So it would have the highest value for I. It would take the most energy to get it to rotate. So therefore, it would rotate at the slowest rate. The disk has less mass distributed at the radius of the size of the object because you've got some mass in the middle, but it still has a large rotational inertia. This solid body, however, has most of the mass distributed around the axis. Okay, so therefore, if I were to roll these all down at the same time, the solid sphere would go first. Okay, again, this velocity would be the highest because I would be the smallest. The solid disk has a moment of inertia of 1/2 mr squared, and the hollow disk would have a moment of inertia of mr squared. So the shape of the object actually can determine how fast it's going to roll down. And of course, that is really due to how the energy is distributed. When it rolls down, the ring has the most amount of rotational kinetic energy for its mass. That's because its mass is all distributed away from the axis of rotation as much as possible. The solid ball, just the opposite situation. It rolls the slowest. Now, again, when we're dealing with rotational systems, we always want to, in conserving energy, take into account any energy gain or energy loss. We do that by saying the non-conservative work done on the system or object is equal to the change in translational energy plus a change in rotational kinetic energy plus a change in any potential energy. Okay? So if energy is added or taken away from the system, it will result in that change in the overall mechanical energy of the system in terms of kinetic and potential energy. We've seen this previously. If there is no non-conservative work, then we can just say mechanical energy before equals the mechanical energy after. For these problems, like many of the energy problems, we choose 2 points of interest, a beginning and an end. What is it doing at the start? What is it doing at the end? And identify what forces are conservative, and if present, if there are any non-conservative forces present. Again, we write a general equation for the work energy theorem, and then we solve for the unknowns. What's unknown? Maybe final velocity, maybe final height, maybe something else. But again, doing this conservation of energy law allows us to keep track of where the energy is going and see how it's distributed among the different types that we have. Non-conservative work, rotational kinetic energy, translational kinetic energy, or even potential energy.